Imagine a world where the most complex, seemingly unsolvable problems in physics, medicine, and cryptography are cracked in mere moments. That's the promise of quantum computing. But here's where it gets controversial. If these machines are answering questions that even the world's most powerful supercomputers can't tackle, how can we trust their results? After all, if something is unknowable, how do we verify it's correct? This paradox lies at the heart of a groundbreaking study by Swinburne University, published in Quantum Science and Technology. https://iop.org/article/10.10825895565 ADFE16. The challenge is staggering, as Alexander Delius, postdoctoral research fellow at Swinburne Center for Quantum Science and Technology Theory, explains. Some problems would take millions, even billions of years for today's fastest supercomputers to solve. Quantum computers, however, claim to tackle these in a fraction of the time. But this is the part most people miss. Without a way to validate these results, we risk building a house of cards on unverified foundations. Enter the Swinburne team, who developed a method to validate the outputs of a specific quantum computer called a Gaussian Boson Sampler, GBS. GBS uses photons, particles of light, to compute probabilities that would otherwise take thousands of years on a supercomputer. The team's method allows us to check, in just minutes on a laptop, whether a GBS experiment is producing the correct answer and identify any errors. To test the approach, they validated a recent GBS experiment that would take at least 9,000 years to replicate on existing supercomputers. The results were eye-opening. The GBS probability distribution didn't match the expected outcome, and additional noise in the experiment went unanalyzed. And this is where it gets even more intriguing. Did these errors strip the quantum computer of its quantumness? Or is replicating the alternative distribution simply too computationally hard? Answering this question is critical. If we can develop scalable validation methods, we're one step closer to error-free, commercially viable quantum computers. As Delius puts it, this could revolutionize drug development, AI, cybersecurity, and our understanding of the universe. But it's a Herculean task, one that requires not just innovation, but also rigorous verification. Here's a thought-provoking question for you. If quantum computers can solve problems beyond our current comprehension, should we trust their answers without fully understanding how they arrive at them? Or is verification the non-negotiable price of progress? Let's discuss in the comments. I'd love to hear your take. For more details, check out the full study, Alexander S. Delius et al., Validation Tests of Gaussian Boson Samplers with Photon Number Resolving Detectors, Quantum Science and Technology, 2025, DOI, 10.10.8.25.89565 AD, FE16, https://this.org. Note: this content is for informational purposes only and is subject to copyright. Reproduction without permission is prohibited.